Hey everyone, I'm going to share my
Hi,
screen.
hi, Bhavna.
Hey,
So let me give you a quick intro and then I'll give it over to you.
sounds good.
Okay, so moving on to our next session, try your hand at machine learning for security. We have Bhavna Soman here. She's a senior security research lead working at Microsoft Defender research team. In her day job, she develops machine learning models to classify malware in real time. So in the past, she worked in the field of threat intelligence and loves to play with natural language processing algorithms. She also holds a master's degree in computer security from Georgia Tech and is also a trainer for malware reverse engineering with BlackBerry. It's really awesome to have you here, Bhavna. So over to you now.
Thank you so much for the wonderful introduction, Nimisha, and thank you to ShaktiCon for inviting me over. I was actually very interested in listening to the last presenter, Mehernush, and I was very happy that she was talking about another application of machine learning and security, because that is a domain that I love, and I'm excited to share that with you as well. All right. So I think you all should be able to see my screen now. So I want to start by talking about how I got here. The previous presenter shared yet another use case of machine learning and its application in security. And I think I'm seeing that revolution happening in more and more areas of information security. And the fundamental reason that's underlying this is that security expertise is scarce, and machine learning is like a really simple and powerful tool to help defenders scale their resources and accomplish their goals, whether it's protecting their customers or discovering better attacks, etc. um, there is a parallel between what is happening in the security machine learning space with what happened a while back with automation. So for example, about 5 to 10 years ago, we saw this SecOps became a commonly used term, and it was more and more accepted that some amount of automation and coding skills is really, really useful for security researchers to have, so that they can really magnify and multiply their impact. So I think from there, similar to that, we're seeing this movement to ML SecOps, where the knowledge of ML and its applications in security is becoming much more useful, where, all security researchers and engineers are kind of touching aspects of ML. And this type of, it kind of becomes another tool in your arsenal, if you will. So this is why I feel very passionately about this subject, and I'm excited to be here today. My agenda for this talk is I'll begin by giving a bird's eye view of the various applications of machine learning and AI in security that I have seen in the industry. I'll talk about the common building blocks of ML-based solutions that are used, and then I'll talk about the specific challenges of applying machine learning to security. And then I'll conclude with a few different examples of different types of applications of machine learning in security. Firstly, I want to talk about these different categories in which I see applications of machine learning and security today. This is not an exhaustive list, just some common areas. So the most common type of machine learning application that you will see is classification or supervised ML. So in this use case, typically you have a labeled data set, and then you train a classifier to identify similar things. So maybe you have a set of files that are clean. Some of them are labeled clean, some of them are labeled malware. And then you want to train a classifier to distinguish between other clean and malware files. This type of machine learning is commonly used for other entities like files, domains, behaviors, etc. In the technical sense, you will see a lot of linear models applied here, like average perceptrons, and also there are some deep learning models applied here, but there is a limitation there, in the sense that deep learning models will usually, they'll be heavier in terms of the compute they require and the training times, etc. So that kind of limits their use a little bit. And there are others as well. Since this is the most basic use case, throughout my presentation today, I will use this example to illustrate different concepts and challenges, etc., like the binary classification of files. The second most commonly used use case is unsupervised ML. So, we saw this in the last talk where the author was talking about anomaly detection to detect attacks against IoT systems. So that's an excellent example of using unsupervised ML. In general, it is used in cases where you're trying to detect some kind of new badness where you don't have a labeled data set. Clustering is another example where unsupervised ML is used. For example, if you have multiple behaviors, entities, files, etc., that belong to a campaign, clustering techniques can be used to kind of group them together and maybe present them together to a security analyst to look at, for instance. In the previous talk, the clustering methods that were mentioned, she specifically said that, hey, this is one thing that does not require the cluster number to be mentioned. So that's like a class of methods that are non-parametric. And that's really important because if you don't have good labels, you don't have a good way of saying that, what the number of clusters will be. So, that's kind of a type of technique that's used commonly. Now I move to some of like more advanced use cases. For these types of applications, sometimes you see them in product, but it's not very common. You definitely see them in academia and in industry research labs. Adversarial ML is a big one. There are several papers from academia around evading existing detection systems. So they will build ML models that, that are able to give an output that will help an attacker evade an existing system. Like, there have been papers around like how to evade an AV engine using adversarial ML. And the converse of this domain is robustness. How can we build better ML models that are robust against such adversarial attacks? How can you protect against data poisoning or model inversion, for instance? Another domain is interpretability. So this is really critical because a lot of times customers don't directly trust the output of an ML model, and they want to understand, why something was called suspicious or malicious. So this set of techniques helps you reason over the outcomes and build some kind of explainability into the output of the ML model. And another domain that I want to talk about is reinforcement learning. So again, this is very research oriented and I haven't seen applications in product, but there is research around like, hey, how can we provide personalized protection using maybe the contextual bandit problem, or can we build an automated red team system using reinforcement learning, or even an automated defense system? So these are some categories in which ML is applied in security today. I want to open with an example of how, and this is from my work, where we built a classical ML model to protect against an attack from the Ursnif botnet. So this was a small scale targeted attack, and like the graph kind of shows you, like over time, the prevalence of the files that were associated with this campaign. It was targeted towards small businesses, and the attacker did something interesting where they tailored the name of the document to the victim that they were sending it to. For example, the Dolan Care Statement.doc, it was a macro-enabled document that was sent exclusively to victims in a specific city in Missouri, US, where Dolan Care is actually an elderly care assisted living facility. So they were kind of disguising themselves as a receipt or like an invoice from this particular company that's a real company in that area. And obviously, like the document itself, it wanted the victim to enable the macros. And then once you do, this obfuscated PowerShell will get launched, which will connect to a domain and download the payload, which is the Ursnif botnet. And, you can see that like in the different cities that they were present, they used different lures that were specific to that city. So for example, in Nebraska, they used DMS, which is the landscaping company there. In Missouri, they used Dolan Care, and then in Tennessee, they used Dockery, which is like a flooring company there. So they were customizing, this type of attack that they already had. So here's how machine learning helped in protecting in this specific case. So we had one set of models that were running on the client. Like these are very lightweight linear models that don't give a verdict, but they kind of give like a suspicious or not suspicious verdict instead of malicious or benign. So if that model says that the file is suspicious, then it sends like a larger section of metadata about the file itself up to the cloud. And then the cloud will apply like a series of models to it. So the two specific models that I want to talk about are the model that is specific to macro files and the one for non-PE files. In this case, both of these models said with a higher degree of probability that the files are malicious, and then the cloud, sends a verdict back to the client, and the file gets quarantined. So now I want to deep dive into the features and kind of understand how this model is able to decide that this file is malicious. This model used three broad categories of features: expert features, fuzzy hash-based features, and contextual data. So expert features, you can think of them basically as researcher signatures, but low fidelity researcher signatures. So any one of these signatures will not really say that a file is malicious or not, but it definitely says that the file is suspicious. So an example of that is maybe like the file has a certain import function, or maybe it is changing a certain registry key, and you can see that through the strings. So that is an expert feature, and it might not always hold true that a file that is touching that particular registry key is malicious, but it becomes a signal to the classifier and says that, okay, I need to kind of think more about this file. So those are the expert features. And then the second type of features is the fuzzy hash features, which is basically, the rolling hash of the content of the file itself. And then the third type of features is the contextual data. And so these features are, where was the file coming from? Which folder did the file land into? What is the name of the file? Is it similar to other legitimate names? And what's the distance between all of that? So those are some of the contextual features. Now you can see here that the expert features and the fuzzy hash features really contributed highly to saying that the file is malicious, whereas the contextual data was not able to make that much contribution in the malicious verdict. And that makes sense because we saw earlier that the attackers were modifying each file to kind of make it look kind of real. So therefore, the contextual features in this particular case were not powerful. But as you can see, that's the power of the machine learning model. Since it is considering all of these signals together, it's still able to detect the file as malicious. So now I'm going to talk about the building blocks of a machine learning algorithm. So these are like the basics that you need to cover if you want to build a machine learning algorithm. The first thing that you need is data. And then we'll talk about various features that can be leveraged. We'll talk about how to fit a function and what that really means, and then evaluating the efficacy of your model. So let's talk about getting the data. The most common type of data set that most people start out with when they are getting introduced to machine learning is the toy data sets. These are usually packaged alongside Python packages or data libraries. So an iris data set is a really good example. So especially when you read blogs about different machine learning algorithms, these are the data sets that most of them will be leveraging. Now, for our security use case, there are some really good open source data sets available. So if you want to try your hand at machine learning for security, these data sets they have been released by companies. They mimic the real world, and in that sense are very useful for building realistic conclusions, realistic algorithms for security. So the first one here is the Ember dataset, which was released a few years ago by NPM. It has about 1 million files, and when it was released, it was the most comprehensive malware file dataset. The second dataset is much newer. It was only released, I think, in December last year or January this year. Sophos and Reversing Labs came together to release a larger dataset, which has about 20 million files, and it also has some amount of behavioral information. So it's pretty comprehensive, and a lot of research teams have now moved to experimenting with this dataset. Microsoft also released a data set a while back on Kaggle as part of their malware classification challenge, but at this point, that data set is a bit outdated. And then obviously there is real data, which is hard to get. But short of getting actual product telemetry, VirusTotal is a really good real-world data set that has been useful in experiments in my experience. Through the API, you can get large-scale data. It is a bit biased towards malware versus clean, so that is something you'll have to account for. But in general, it's kind of like a good real-ish source of data. And then the last one, obviously, is product telemetry. So this is This is not usually shared with outside audiences because of restrictions around privacy and compliance. But the most realistic assessments and practical applications come by experimenting on this data. Cool. Now we're going to talk about feature extraction, and I'm going to solicit some audience participation. So I know that this is, we started doing conferences virtually, but I still want to enable audience participation. So I want to ask all of you to go to menti.com and enter this code, and then I'll ask you some questions, and then, we'll make some word clouds with the answers that you give. I'm going to stop sharing my screen for a second. And go to menti.com myself. Okay, so here, what are some useful features that you can use to classify malware files? So just go to that website, enter that code, and then you'll be able to enter outputs, enter some words, and this will automatically generate word clouds. Awesome. Yeah, these are all good answers. Import functions, PE headers. Yep, signer hash file extension, really good. Awesome, really cool. Okay, so let the algo find it. Nice, yeah, code, spyware. I love this. Thank you all for participating. Yeah, linkers. Okay, there are several really good answers here. I'll give it 10 more seconds and then I'll move to the next question. Nice. So yes, it's really easy to come up with all of these features to classify malware files. Let's try one more. What are some useful features to classify malware domains? Let's think about a different set of features. If you want to classify domain names, how could you do it? Yeah, TLD is a good one. Entropy, excellent. Actually, that's relevant for both files and domains. Yep. Length, who is, domain name registration. Yep, that's really good. Name servers. Nice. Ngrams, yeah, that's a really good one too. Org info. Okay, I'll give this 10 seconds and then I'll go back to the deck. Misspelled words, also a good one. Dig URL, yep. Protocol, HTTP or HTTPS, nice. Okay, excellent. I will go back to sharing my deck. But thank you for the participation and thank you for the answers. That's exactly what I was trying to get.
Hey, Bhavna. So I'm reminding you there's 5 more minutes.
Oh, didn't I have 1 hour?
Oh, sorry, my mistake. Sorry, my bad.
Okay, good. All right. So yeah, we all had good answers, but this is just an example of like, hey, there are a lot of features that you can use for malware classification or domain classification. And then some of you also pointed out that you don't have to do manual feature extraction. There are machine learning techniques that will do that for you automatically. The downside of that is that you lose out on some explainability sometimes. Okay, so let's talk about curve fitting. So machine learning, sometimes it can appear as a daunting new domain, but let me tell you that it is just glorified curve fitting. And if you've ever done a class in numerical analysis or linear algebra, then you've done some curve fitting, and that's essentially what machine learning is at its very core. So this is a really simple example of how you would build a linear model. So you have an input that is the x variable, and then you have the output, which is a y variable. And you can see it plotted in the green dots in this toy graph. And then you can imagine that if you wanted to plot a linear function to fit the points, then you'd have to define the parameters of this line b0 and b1, and then you would use numerical analysis techniques to find these parameters such that the error is minimized, so that the distance between the points and the line itself, that is minimized. So that is kind of essentially like this is how you would fit like a linear regression model. Obviously, like practical machine learning is a bit more complicated. So I want to talk about just two different types of functions, that would be used more commonly. So the sigmoid function is, very commonly used specifically for binary classification problems, like the kinds that I usually work on, which is the reason that it's used is it's easily differentiable, and also that it gives an output that is 0 or 1. So, the binary problem is helped there. And then the second one I talk about is the ReLU function, which also has a similar effect as the sigmoid function in the sense that it's binary, but also the computation here becomes much more efficient. So when you have a neural network which has multiple nodes, and you have to do similar like computations for or fitting at each and every node, then the ReLU function, which optimizes or makes the computation more efficient, it becomes much more lighter and makes the training of the model much faster. Awesome. So the next thing I want to talk about is evaluation. Evaluation is like really tricky compared for the security use cases compared to usual machine learning use cases. The first question you want to think about is, where is your ground truth? And this kind of relates to the challenge of getting labeled data, good labeled data in security. Usually you'll have noisy labels. You have to decide how you're going to get it. Is it going to be through graders, or is it going to be through some kind of data sets that I talked about? So that's a question that you'll have to answer. And then the next aspect to consider is that your data set will usually be very unbalanced, in the sense that so for example, if you're building a file classifier and you have 10,000 files in your organization, 99% of those will be clean. Only 1% of those will be malware. So how are you going to build a classifier so that it is able to know that most of the files are clean, but also get enough signal so that it's able to say that, okay, some files are malware, so that it can identify the malicious signal. And this unbalanced problem also affects the metrics that you can use. So for example, if you just use accuracy for this type of a problem, then, because 99 out of 100 files are already clean. So if you have a naive classifier that just says everything is clean, it would already have 99% accuracy. And obviously this classifier is totally useless because it's not going to find any malware. So which is why we use things like precision recall and FP rate. So let me tell you what precision means. Simply, if your precision is say 0.7, then it means that for every 100 files that your classifier says is malware, only 70 of them are actually malware. Then recall, it can be defined like this. So for every 100 files that are malware that are seen by your classifier, so if your recall is 0.7, it means that only 70% of those files will actually be identified by your classifier, and the remaining 30% will be, they'll be misses, and your classifier will not detect them. Another important metric that you want to look at is the false positive rate. So for example, if your false positive rate is 0.3, that means that for every 100 files that your classifier says are malware, 30 of them are actually not malware. So this is a very critical metric for machine learning applications that are deployed in production, because organizations can be very sensitive, because every time you have a false positive, say you block a file as malware and it wasn't, someone, they downloaded a file and they can't use it, or there was a business critical application that they're not going to be able to use anymore. So that is considered very, very disruptive. We also use like F1 score, and the PR curve can be used to plot performance characteristics and determine the probability threshold. All right, now I'm going to talk about some of the major challenges that we see in applications of ML and security. So the first one is labels. The lack of or the noise in these, the scale of the data and the features themselves. Measuring actual customer outcomes is also very tricky. I'll talk more about all of these, including the changing landscape in the malware, as well as the clean files, adversarial evasion, and then false positives, which I mentioned just now, where those are like sometimes a bigger problem than false negatives for customers. And then finally, interpretability. So let's start with labels. This is pulled from Microsoft Defender's telemetry. So 96% of the malware that we had on our systems was seen only once and never again. So that's a huge, huge percentage of files that are just seen only once on your system. So it's really hard to get good labels in this type of environment. So you can see that only 3% are seen 2 to 10 times, and only 0.01 are seen on more than 1,000 files. And only a small percentage, you can get good labels from external data sources even. So obviously, if you want to train a machine learning classifier, how are you going to give it adequate exposure to the diversity of malware features, while at the same time, keeping your labels less noisy and accurate? This is a huge challenge for, across the classification or supervised ML domain in security. The second challenge is scale. So for Microsoft Defender, for instance, when we are looking only at file encounters on the client side, across the environment, we have millions of files that are seen every day. So at that stage, the model has to be extremely lightweight, and it has to be able to have a small memory footprint so that it is not taking away memory from the client. It has to have a small compute footprint so that it's not taking away processing power from the client itself. And then the inference time has to be very fast, because if someone is using their computer and they're waiting for like 2 or 3 minutes to open their file while the AV is checking it or something, they're not going to like that experience. So it has to reply within milliseconds. And the same holds true for any real-time model, even whether it's at the client or the cloud. You have to give your inference time is very, very short for it to give a good customer experience. And then we can have like heavier models, but usually we use them in a slightly offline setting, where, for example, if a file is suspicious enough, we'll collect the sample, detonate it, run a deep neural network on it, and then send a verdict back. But usually that takes minutes or sometimes even longer. So those models, so that's kind of like how you want to think about the problem of scale at different stages of this defense in depth kind of pipeline. I want to talk a little bit about measuring actual customer outcomes. So now let's say that you have built a model and then you've deployed it to the customer, and now it's looking at all these new files and it's giving verdicts out on that. How are you going to determine how it's doing? Because you might not see some of these files ever again. You may not get access to any of these files because they're the customer's private property. So one way to do it is manual grading. So in this case, obviously you have access to a certain set of files, and you manually have some researchers look at and say that, okay, this verdict was right, this was wrong, etc. Another way is to then automatically extrapolate from that, manual grading. So for example, maybe you grade 10 instances, and then, you can say that, okay, these 50 are similar to these 10 instances. So I'll consider, applying these grades to this extended data set. And then, customer submissions is always a good option, where, the customer will say, hey, this is an FP that, you've detected wrongly, or this is an FM that you didn't detect. But obviously, if you get to that point, it's leading to a bad experience for the client. The changing landscape is very interesting. In security, we often talk about how the malware landscape is changing so fast, and we have to adapt to that quickly. But one thing that we don't think about is like the temporal drift in clean features. And through our experiments, we've noticed that the temporal drift in clean features is actually more than you see in malware features, which causes, so if a model is allowed to stay stale for too long, then it'll keep having a higher and higher false positive rate because it's not able to judge the new clean features that are coming in. And that totally makes sense because, in this world, there are probably more clean software developers than there are malware developers. So that's another interesting thing to keep in mind. So interpretability is a big one. Usually people will not trust the output of a machine learning model. If a supervised or unsupervised model says that, hey, something is bad, they'll be like, okay, how bad is it? Is it like ransomware bad, so I should unplug my computer, or is it just like a browser pop-up so that I can ignore it for a few more days and do something more important? And then they kind of want context around, okay, what attacker is this associated to? What should I do? What's the next thing that I would expect this type of attack to go? So all of these things can be addressed using interpretability methods from machine learning. Adversarial evasion is something I touched on earlier, and this is a huge challenge as well. Now that more and more applications of machine learning and security are prevalent, the attackers are catching up and they are exploring ML-based methods to evade these models and these detectors. But obviously, there are like the traditional methods as well, like more sophisticated packing or obfuscation. So now that we've covered the challenges of applying machine learning and security, I want to share some examples with you and go into the depth of how we do some of these things. So I showed this example to you earlier where this classical linear model was used to block the ersnif botnet. So here's how the process of building this model goes. The first step is selecting samples. We have millions of samples. We want to select like a small subset of known clean and malware files, and then you want to fine tune the ratio of clean and malware to ensure that the model should understand that most of the universe will be clean, but also has enough malware signal to discriminate between malicious and clean files. We might also want to target sometimes specific file types, like we had that macro specific model, for instance. Then the next thing is feature selection. So you all had excellent ideas on, how feature selection can work. In general, features can be related to any of the machine's attributes, dynamic or contextual attributes of the file, static features of the file. And how we do it is that we extract millions of features, for a set of data, but then we have to do feature selection or some kind of reduction because at that high dimensionality, the computation for the training of the model will not be feasible in a reasonable amount of time. So we kind of do some meta-analysis to say which features are more important, which features have more discriminative power, and then we downsize to just those. And then, we do the kind of experimentation, hyperparameter tuning that is part of every machine learning model. You try out different models, you try out different ratios, and then the one thing that we have to do again is tuning the probability threshold because we know that customers are really sensitive to false positive rates, and we have to maintain or we have to tune the operational characteristics of the classifier such that the false positive rate will remain low. And then, first we ship it in this quote unquote experimental mode where it will kind of be looking at the traffic, but not giving blocking verdicts. And this is when we kind of evaluate the actual outcomes that the classifier is able to provide on new unseen traffic. And then if it is performing up to par, then it will be turned to a blocking mode classifier. The second example I want to give is how we use ensemble models for malware classification. This was work done by my colleagues Jugal, Holly, and Randy. The idea of ensemble learning is that to build a prediction model, instead of just using a set of classifiers, we can bring these classifiers together. We use a set of simple base classifiers, and then we bring them together to this stacked approach so that the one machine learning model can decide, based on these signals, which are more accurate, which are less accurate, and then give a final verdict. This is how the architecture of an ensemble classifier could look like. So maybe you have a set of base classifiers. For example, there was the macro classifier. There might be one that's focused on behaviors, one focused on contextual features, and you have all these base classifiers that give their own prediction. In our case, we were using their prediction in terms of the probability of something being malware. And then you feed these predictions as the data set into a new classifier, which then, gives the final verdict. There are several benefits to using an ensemble model. The first of which is that it filters out noisy signals automatically from any underperforming model. So if one or two models within that set of base classifiers is noisy, then the stacked classifier will be able to smooth out that noise. And the second thing that's very interesting, that's an interesting side effect, is that it increases the predictive power, but also adds some explainability. So, for example, if I have a stacked classifier that has a number of base classifiers, maybe one of them is for contextual features, maybe one of them is for fuzzy hash-based features. So then, after I get the output from the stacked classifier, I can easily say that, okay, this file was malicious, but it was malicious because of, it was in a suspicious context, or because the fuzzy hash was looking bad and it was similar to bad things. Whereas if I had, combined all of these features directly into one classifier, that interpretability becomes a bit more complicated. And then it adds resilience against attacks on individual models. So we talked about adversarial machine learning and how attackers are exploring that. Ensemble models, because it's a combination of multiple models, it adds some resilience as well. I'll give one more example, and this is very different from the stuff that we've discussed so far, which is an application of natural language processing for threat intelligence. So I want to introduce the concept of named entity extraction here. So this is a blob of text, and if I feed this into like a named entity extractor from Azure or Google, it can extract like entities like this, which would be, say, Sansa Stark is a person, Eddard Stark is a person, Winterfell is, an organization or a geopolitical entity. So this is what named entity extraction looks like. You feed in a blob of text, and then, it automatically extracts the significant entities that are present in that text. Now, if we look at a security related text, this is an APT white paper about a China-based actor. What happens here is that the entities that I would like to extract from this are, the names or the aliases of the actor and the techniques that and the MITRE techniques that it's using. But obviously, the off-the-shelf named entity extractors, since they are not tuned to the cybersecurity domain, they're not able to do this type of stuff. So this kind of example is about training a named entity extractor custom applicable to the cybersecurity domain. And the reason we did that is because we want to generate these security knowledge graph type of structures. So for example, if I can run like a named entity extraction model and build relationships across documents, I can automatically build like a security knowledge graph. So this graph in particular shows the overlap in MITRE techniques used by Emotet, which is a commodity malware family, with some APTs. And, so this kind of work is something that threat intelligence analysts do a lot. So building machine learning techniques to create the security knowledge graph automatically is potentially a very powerful thing. To construct the training data of this data set, because we're now in the NLP domain, it's a totally different technique. Instead of having like clean or malware labels, we have this labeling technique called IOB, or inside-outside beginning. And so this is an example of how that would work. So Eddard Stark is the phrase that indicates the name of a person. The first token in that phrase will be B-person, which stands for beginning of person. And the second, or all subsequent tokens in that phrase, will be tagged with I-person, which is inside a person. And all the tokens that are not in any of the phrases that we care about or entities that we care about will be tagged with O, which means outside. So here is an example of a sentence from the cybersecurity domain about the numbered panda actor. And here is how it would get labeled in the IOB context. So numbered panda is the bad actor phrase. And numbered is the beginning of the bad actor phrase, and panda is the inside of the bad actor phrase. And all the subsequent tokens are, outside, etc. So again, in the feature extraction space, we have a different set of features here. So we use some traditional NLP features like, part of speech, lemma, word type, etc. And then we also have some unsupervised features, which is word embeddings. In very simple terms, word embeddings are vector representations of words in text such that their meaning and semantic relationships are captured by the numerical vectors. So for example, if two words mean the same thing or are used in the same context a lot, the cosine similarity of their vectors will be high. So this particular word embeddings model was trained using Word2Vec on like a corpus of TI data. So think security blogs, APT white papers, incident response reports, etc. And this is an example of how well the word embeddings worked in this context. So this is a visualization of the embeddings in TensorBoard. And since our embeddings were trained on documents related to the cyber domain, the clusters of points that are formed here are related to the context in which the words appear. So for instance, the closest 4 points to APT28, 2 of them are its aliases and 2 of them are other campaigns related to it by attribution. This was the architecture of this solution where we had our corpus of blogs, white papers, the text. We had some simple HTML and PDF parsers. We did some minimal text processing just to clean out, and then we extracted the word embeddings. We split it into a training and test data set. We did the custom feature extraction, which I told you about, like the traditional NLP features, and then added the word embedding features as well. And then we experimented with 2 different models here, CRF and LSTM. CRF is more like a linear model that is applied to a sequence problem, and LSTM is a special type of neural network that is also applicable for sequence problems. They're both very widely used, specifically for language models. This is how we evaluated the model. We measured the positive precision and recall. And here you can see that the positive precision was pretty high across the board for all of the models. But the recall, the LSTM was kind of doing better in terms of the recall. But then, we looked at these metrics on specifically unseen tokens. So these are the tokens where these tokens were not present in the training data set at all. So these are just net new tokens. And we want to see how the model does in terms of identifying these using the context in which they appear. So here you can see that the CRF with embeddings, it performs the best. And it was the only model that had any manner of positive recall. So hopefully I've given you like a diversity of like examples and kind of piqued your interest. If you want to learn more, the basic machine learning course on Coursera by Andrew Ng, it's really the best. He is not only like a great visionary of the field, but also a really good teacher. The malware data science book by Joshua Saxey, again, a really good resource, but very specific to the malware classification problem. Kaggle is a data science platform where various organizations provide data sets and kind of define a data science problem that they want to solve, and then everyone can try their hand at solving the problem, optimize their solution, and then usually a lot of people will also share their solution. So it's a great place to learn about applying ML. And the last thing is CAMLIS, which is the Conference on Applied Machine Learning for Information Security. It's a relatively new conference. The last edition was in 2019. They didn't do one last year because of the pandemic, but I think there's going to be one more in 2021. So yeah, these are some things that you can use if you want to learn more about the space. And with that, I will leave some time for questions. Hey, so I don't see any questions.
Yeah, there is still a question. I'll read it out for you. we are using ML in security, is ML secure in itself?
Yeah, so that's a great question. Like all systems, ML is not perfectly secure, and I think I talked about some of the adversarial ML and how different machine learning techniques themselves are used to attack other machine learning based detection systems, and there are several academic papers on that. But it's an evolving space. It's not secure, but there is research around robustness, on how to protect against different types of attacks for machine learning. So yeah, it's a powerful tool, but it's not perfect at all.
And what are your thoughts on using machine learning for phishing attacks?
Phishing is actually one of the first few applications where machine learning was applied. So it's definitely very applicable, and you can use multiple different types of techniques. You can apply machine learning to the context, the full email content, the arrival of the email. There is even research around applying machine learning to detect brand impersonation. So, a lot of phishing emails will try to impersonate like legitimate brands to get people to click or enter their password, etc. So, yeah, phishing has definitely a lot of applications of machine learning.
Next question. What are the algorithms used for feature selection in malware detection? Example, PE headers data. Since the use case is critical, did it often require manual intervention?
So this is a really interesting question, and different people have different approaches here. I think what has worked so here's what will happen. You can usually build a deep learning model that will automatically select the features under the hood and will produce really good performance. But the problem with that is that deep learning models tend to be heavy and less efficient. They require higher compute, and they need more processing. So what happens is that usually what I have seen work better to build lighter weight models is to have like a security researcher who is an expert in the field and who can identify features. So keep in mind that by features, I don't mean like each and every PE header that you have to like say whether it's a feature or not, but you can just say that, okay, I'm going to look at this field that contains all the PE headers as a feature, or I might extract like the n-grams from this particular field and use that as features because I think there is interesting information here. So there are multiple ways to do it, and there is no right or wrong answer. It really depends on your use case, essentially.
Next question. 3 reasons why machine learning security techniques over other security techniques. Why machine
So
learning security techniques?
um, maybe the question, I don't quite understand this question. So machine learning's applications to security I'm not saying that they are necessarily going to, okay, so this is what I understand the question. Like, why do you want to use machine learning based protections and defenses rather than just using the traditional side? The biggest reason is that the scale of the problem of defending the internet that we have right now is very, very large. So it's not always possible to use like the traditional methods. So for example, at the speed that the malware landscape is evolving, like if I had a huge team of security researchers who were building really good generic signatures, but it would be really hard for them to keep up with the scale that we have. So that is the power of machine learning. Like it can help defenders scale, but obviously there is a downside. Like these algorithms are not perfect. They suffer from bias. And they need a lot of work to maintain. And also I think the most critical thing is that in terms of discovering new attacks and in terms of like protecting against newer attacks, like just traditional security researchers and those kind of techniques have shown more efficacy. But at the same time, there is a large section where these machine learning techniques are applicable, and what happens is that applying these techniques can free up your security research resources so that they can focus on the newer or higher criticality problems.
Okay, next question. Sometimes our datasets need protection and can't be known to everyone. how to ensure security of datasets through ML?
That's a really interesting question. So one way to interpret this question is that, like, how can we make sure that our machine learning algorithms are not breaking the privacy of the underlying data set? And that is a whole domain, under fairness and responsible AI, where we want to have privacy preserving AI and ML. But um, maybe the question also means that how do you defend data that is stored in various servers using machine learning, or maybe how do you prevent data exfiltration using machine learning? So there are definitely series of techniques, particularly using anomaly detection, which look at the operations that are taken on data sets. So for example, I might have a sequence of operations that were taken on a data set, and I might, build an anomaly detection on that. So for instance, maybe I have maybe I have a SharePoint server where, a certain team accesses these documents regularly, but then one day I see a person from just a totally different team access that data, and that event kind of triggers the anomaly detection. So those kind of applications also exist.
Next question. Could you comment on the quality of open source datasets for ML in security domain?
Yeah, absolutely. So that's a great question, because if we want researchers and academia to do good research for ML in the security domain, we need to provide them with good open source data sets. And in the beginning, there were a lot of restrictions around privacy and compliance that prevented companies from sharing this data. But recently, some companies like Sophos, they have made huge strides in that regard. So the Sorel data set that I mentioned, it is a really high quality data set that can be used for training almost real life machine learning models. I haven't experimented it with myself, but it seems really comprehensive.
Next question. In the beginning of the talk, you mentioned contextual based features. Can you elaborate on that?
Yeah, so by contextual features, I mean, looking at the context in which a particular file appears. So was it downloaded from the web? Was it downloaded from an untrusted website? Was it, which folder is it in? What kind of name does it have? So all of these features that have nothing to do with the content of the file, or, what actions it takes, but it's just like, what is the context in which it appears? Because, for example, if like this file that you have just downloaded from an untrusted website, if it if it appears in the system folder with like a really similar looking name to a legitimate file, then that is inherently more suspicious than something in the downloads folder, for instance.
Next question. Has Microsoft explored computer vision techniques for malware bytes data?
So we have done some experiments using to apply computer vision to like just the distribution of malware bytes. I think I remember seeing like some open source blogs as well on it. But in general, those techniques were not found to be efficient for the production context. So they're not used in production because, frankly, for malware classification, I mean, why would I use like computer vision if I can just get really similar performance using linear models? So that's kind of been the driving force so far. But there is some research around that space.
Next question. Windows Defender use layered machine learning models. Can you describe that?
Yeah, of course. So the layered machine learning models in Defender, I kind of shared one slide on that. But what happens is that there is one layer of machine learning models that sit on the client itself. These are typically very simple models, and they will usually not give a malware or clean verdict. They will only say suspicious or not suspicious. And if something is found to be suspicious, it will, like, a certain metadata package will be sent up to the cloud. And that is where like the majority of our machine learning models live. Usually they are linear machine learning models, average perceptrons, boosted trees, etc. But there are some deep learning models that we have recently deployed to the cloud as well. So these models will look at this metadata vector and will say whether a file is malware or not. And so far these models are very they'll give a quick response. They're highly efficient. If even these models are not able to give a good verdict, and they still, put the file in a certain bucket of suspiciousness, then we'll request the sample, and then we have some deeper, some neural networks, DNN based, that will look at the sample itself, analyze the static features, detonate it, and use all of these features to say whether the file is malicious or not. So these are kind of the various layers that we have in the defender land.
And there is a question in chat. Can a ML model be reverse engineered? I think that's what they mean.
So I think it is possible to sort of reverse engineer an ML model. So one of the things that I have played around with is, once a machine learning model has given an output, or, a series of output on my inference data set, then I can, reverse engineer what are the features that were important in that context. Why did a certain file get classified as malware? And I can see which features contributed to it being classified as malware. In that sense, it is possible to reverse engineer some models. But it's not always meaningful, because a lot of times features are, maybe like it's an n-gram of a string or something. So it doesn't give you very much information, but technically it is possible to do that.
Maybe last question. Okay, yeah. What tools can be used to reverse these models?
So there are black box techniques, and then there are white box techniques. I think the stuff that I talked about was the white box techniques, where I have access to the model, and I can inference it on a series of data set, and I can see which are the features that are important for the model, and which are the features that are contributing maximum to the malicious verdict, etc. So tools are just like coding, Python, and just libraries. So you don't need like a specific tool set here.
Last question, Bhavna. What is the latest machine learning applications for security?
Oh, wow. This is a really fast moving domain. So I don't know quite what is like the absolute latest thing. I think the stuff that I have found most exciting is applications of reinforcement learning to security. Again, this has not been seen in the production context yet, but one of my colleagues recently published an open source library where you can simulate RL based attacks and defense models for security. So that kind of stuff is very exciting. How can you leverage machine learning to automatically attack systems, and then in the future automatically defend systems as well? Hey, Nimisha, you're on mute.
I'm sorry. That's it for the Q&A. I think you answered all the questions. So thank you for the informative session, Bhavna.
Awesome. Thanks for having me.